Today our speaker is Vyshegorodtseva, and she will continue her story about dynamical entropy in C-star algebras.
So today I would like to continue my previous talk, and we will start with some motivations of the concept of dynamical entropy. Then we will recall some definitions that we have introduced on the previous talk. And then I would like to tell you more about C-star algebras and entropy in them. So my talk is based, as last time, mostly on the book by Sergei Nishveyev and Erling Stormer. And this book is called Dynamical Entropy and Operator Algebras. So let us start. So the concept of entropy was introduced in 1850s by Rudolf Clausius, and the first definition that was given for this concept is as follows. So the first statement in this on the slide is the original definition of entropy in classical thermodynamics. It was introduced in 1954, if I remember it correctly. And the studies of the second law of thermodynamics shows that the entropy in closed systems should not decrease. So it may stay the same, and then the process is reversible, and if the entropy increases, then the process is irreversible. But this definition doesn't tell us much about what essentially is entropy. And it was and the progress in this field was made by Ludwig Boltzmann in 1870s. He introduced another formula for entropy, which takes the following form. Here we have the Boltzmann constant and sum over all states of probability of each state of the system. So I will explain what this means. He was Ludwig Boltzmann was studying the microscopical behavior of such systems as ideal gas and well, not an ideal gas, but in gases, liquids, and etc. He came up with the following definition. This means that we are taking, so we are considering all possible states of a system. We look at its probabilities, and so this sum over all states of its probabilities is our entropy. So it follows from this formula that, for example, if we have n states with equal probabilities, then the entropy will increase as n increases, which is quite intuitive because so we would like to. So what entropy is? I think I haven't stated it. So in this sense, we can say that entropy is the uncertainty of the system. We have n states, and we would like to predict in which state the system will be as time progresses. And the harder it is to predict this, the higher the entropy is. So I can return to my example with n states. It is indeed harder to predict the next state if we have more states with equal probabilities. I would like to say about this formula that here we have the Boltzmann constant, which is measured which has the following value. It's measured in joules per kelvins, and this constant was actually not introduced by Boltzmann. He just proved that this formula, this sum, is one moment. It's proportional to the original definition of entropy introduced by Clausius. So he proved that, but he didn't think that it is. If I'm not mistaken, he didn't prioritize to count the particular value of Boltzmann constant. And by the way, this is the same Boltzmann constant as we have in the law of ideal gas. So, and the value was firstly estimated by Max Planck in early in the first years of the 20th century, and his estimation was quite close to the value we have nowadays. But this, so the definition of entropy that was introduced by Boltzmann, this function, was studied by mathematicians, but it wasn't a very fruitful field before. In 1940s, Claude Shannon introduced his definition of entropy in the field of information theory. After Claude Shannon introduced this definition, Kolmogorov was inspired by it, and he started studying the dynamical entropy, which we have discussed on the last lecture. But firstly, I would like to talk a bit more about Claude Shannon's entropy, and because it is actually so the definitions that we have discussed last time is a generalization of this definition. So in information theory, we would like to consider the following construction. So imagine that we have an alphabet A, and each symbol of this alphabet has a probability of occurring in our signal. And well, the uncertainty. We would like to measure the uncertainty that we have if we want to predict the information that we will get after we get some signal. For example, let us consider a simple example. If we have a coin and we want to predict which state it will take, if we will get a 0 or a 1, we will be the most uncertain if the probabilities of 0 and 1 are equal, and the entropy or the uncertainty will be equal to 0 if the coin always gives us 1 or 0. I mean, just one of them. Excuse me. So we should say that measuring the entropy is so in this sense we can call entropy the information that we receive, because the uncertainty that when we get rid of the uncertainty, we get some information, and therefore the entropy is the measure of information. When we consider this formula with a natural logarithm, the information is measured in nets, natural units, and if we have a logarithm with base 2, the information is measured in bits. So this is actually very important. This concept is a very important one in information theory. For example, it is very important for us if we want to understand what is the best way to encode a message. For example, if we have a message and we know for a fact that some letters have much greater probability of occurring in this message, we would like to encode them with fewer symbols, and each of these symbols will contain more information. So we can, using entropy, we can count the information that is contained in each sign in encoded message. And so if we therefore, well, when we encode the message in such a way that those with greater possibility have fewer symbols in a encoded version, then our message will be shorter, and in general, I mean, and we will prioritize this over encoding them in any other way. So let us talk about how did Claude Shannon come up with this concept. He was actually generalizing the concept from statistical mechanics. He took an axiomatic approach, and he wanted the function of entropy to have the following 7 properties. So firstly, I don't know if I need to read them out loud. They're pretty obvious. Firstly, the function of entropy should be equal on 2 random variables that are almost surely equal. Other properties include such a thing as continuity. Another one is what I have discussed before, is that when we have an alphabet n, as in my example in about physics, we will have an increase in entropy if the letters have uniform distribution, and if n increases, entropy increases as well. Then we have a property that if that entropy is maximal when the distribution of probabilities on the alphabet is uniform. Other properties include the fact that joint entropy can be expressed as the sum of entropy of one of its elements and the second element with respect of the first one. And the last property is that joint entropy is less or equal than the sum of entropies for 2 random variables, and the equality is obtained when these random variables are independent. So these properties are quite intuitive when we think about how we would like. So when we think about when we get the most information, indeed, if we know that a coin will give us 1, the entropy will be 0, because we know for a fact that it has on the one side, and we don't achieve any information when we make this experiment. And other are quite intuitive as well. For example, well, if if two random variables are independent, so if they're dependent, the uncertainty is obviously less because the uncertainty of the joint distribution, because we can base our assumption about the second one on the first one. And it was proved that the function, the only function that will have all those properties is the function that we were considering. That, of course, if we have, I should have told about the case about physics. If I have a continuous amount of uncountable amount of states, uncountable amount of letters in our alphabets, we will just use an integration instead of the summation, and we will get the same result. Well, and after the works of Shannon's were published, Kolmogorov was inspired by them, and in 1950s he started to study the generalizations of this entropy on his seminar, and which were attended by many prominent Soviet mathematicians. For example, it will be important for us, it was attended by Sinai, who then proved a number of properties of dynamical entropy. So I think we might proceed from the motivations and discuss a bit discuss again some things that we have discussed last time. I will recall some definitions, so you might see that the entropy of a partition is introduced in a very similar way as the previous results, as the previous definitions. And talking about dynamical systems, it can be defined as the supremum over all partitions of the following limit, which exists as we discussed last time. So essentially what we would like, how we can describe the dynamical entropy is that it measures the amount of uncertainty when we want to predict the next state of our dynamical system. So, for example, no, not for example, just when we want to predict the address of tx of a given point x. Okay. Then we can, it was proved by Sinai that actually we can count the entropy in a simpler way than taking the supremum over all partitions, and this way is to take the entropy of generating partitions. And then we can discuss some properties which I think I won't discuss again, but these properties are very similar to the ones that we will achieve later on today's talk. So here we can look at some more properties of entropy of a partition. Okay, and then we were discussing topological entropy, and what is interesting about this entropy is that it was reformulated not only in the form that we can see here using the open covers of X, but also using spanning and separating sets, and this gives us another more intuitive problem idea of entropy. So the more is the entropy, the easier the closed trajectories will go apart. So if we have 2 points that are close to each other, if we have a small entropy, they will stay close to each other. They might stay close to each other for a very long time, and for most of the points it will take place. And if the entropy is large, then for most of the points they will very quickly go apart from each other. So this is another way to think about entropy. So next, we again have a number of properties of topological entropy, which will be generalized further later on this seminar. We know that topological entropy can be expressed using the measure entropy, and that measure entropy can also be expressed in terms of spanning sets. So thus we know that dynamical entropy, but it's okay to call it measure entropy. Okay, dynamical entropy can be expressed, so can have the same intuition as I have just explained. Okay, now I have finished the part about so I have finished recalling some facts from previous lecture, and now we would like to stop for a bit longer time on the following construction that we have discussed on a previous lecture as well. We have discussed it when we talked about conditional entropy, but now we will just need the following fact. So if we consider an partition, which is called zeta here, so when we consider the sigma algebra generated by zeta, we have we can make a one-to-one correspondence between sigma algebras beta zeta and von Neumann subalgebras of L infinity x mu, and so why and we would and we need this fact because in generalization we wouldn't like to consider some partitions, and it will be useful for us to consider von Neumann subalgebras of of sister algebras when we will discuss sister algebras, and therefore we would like to reformulate the definition of entropy in this fashion. We would like to use elements of L infinity x factor zeta mu as to define dynamical entropy. And the way to do it is using the partitions of unity. So give me a moment. Okay. So firstly, we will say that we consider an algebra and okay, we will not consider an algebra, but we will say that we might need to express our entropy, to express our partition as a function of to express entropy as a function of n partitions. and we will start. So if we have x that is sum of x1, x2, and xn, so some other Lebesgue spaces, and we would like to have partitions of x which are expressed using the partitions of the elements of the summons x is, and well, then we will consider firstly an example when we have just one partition, then we will generalize it to a case when we have more than one partition. So let us consider a partition of x, and then if we take the sum of one moment.
Sum of indicator functions.
Yes, thank you. Sum of indicator functions. Then it gives us a partition of unity. Partition of unity in the vector space, and we can rewrite the definition using the indicator function instead of just an element of our partition, but this might not be very convenient for us to choose some special function, the indicator function, and we would prefer to give a definition that looks like the following supremum. We will consider Fi's that are we'll consider partitions of unity consisting of Fi's, and we will take the following sum. Here Fi is the element of one partitions of unity, and the supremum was taken over all possible partitions of unity in our algebra infinity x factor xi. Well, and this supremum, so this is a theorem that this supremum is the same thing as the previous definition. It can be easily seen that the second part of this sum is equal to 0 when we take f that is a projection. If, for example, if we take the indicator function, we will have 0 here, and the sum will be the same, so the supremum can be achieved, and we can discuss why this supremum is not greater than the previous sum. If you would like to hear it after the talk, probably we will have some time for this for the proof of this lemma. Okay, and then we so then we will say that if we take partitions of unity not in L factor xi, but in not in L infinity x factor xi, but in L infinity x, then we will have to take conditional expectation of f is to make a projection, so that this part will be equal to 0 when we have when we have, well, projections. Okay, and again, this is a theorem that this is another expression for the entropy. And yes, the supremum was taken over all partitions of unity in this algebra. Well, next we will discuss this element in our sum. So as we can notice, we often get this at mu fi minus mu at fi. So this expression can be rewritten as the following integral, and this integral is called the relative entropy of measures f de mu and g de mu. And we will soon discuss the generalization of this concept as well. So, and next we consider a case when we have n partitions of unity, no, not n partitions of unity, n partitions of the elements of so partitions of the elements in which x can be okay, in which x can be pictured. I mean, when we take x as some direct sum of some other Lebesgue spaces x is. So it's probably not the best way to call them x is, as we have x e here in another sense, but so this is just a coincidence. I don't mean the same thing. So again, we would like to rewrite the original definition of entropy as the following sum using the product of different indicator functions of x gi's. And the next proposition tells us that for a multidimensional case, we can express entropy as the same supremum as we did before. So we take this again. We take the conditional entropy, and this part, this correction term, will help us to when f EGs are not the projections. So, and supremum is taken again over all families of partitions of unities. Okay. So, as I have explained, this is the idea of. So the idea of this reformulation is to go from partitions of a Lebesgue space to linear functionals. And now I think we can go and discuss a case for entropy. We can discuss entropy for finite-dimensional sister algebras. So let us recall that let us recall that a positive linear functional can be on an algebra A can be written as a trace of product with another element of A, and this element of A will be called the density operator, and we now are generalizing the relative entropy, and the relative entropy will be expressed in the following way. We'll have a trace of q times q phi times logarithm of q phi minus logarithm q psi if phi is less or equal than lambda psi for some lambda greater than 0, and the entropy is equal to infinity otherwise. Then the first properties that we can discuss is that when we have two values, lambda 1 and lambda 2, the entropy of lambda phi, lambda 1 phi and lambda 2 phi is expressed as follows, and then when we consider the density operator and rewrite it in this fashion, we will see a new not definition, but so we will have the following expression that an entropy can be described in this way, and this is, as you can see, the generalization of the definitions that we have of the very first definitions that we have discussed today when we were talking about entropy in thermodynamics. Well, a trace, as we know in quantum mechanics, is generalizes the concept of integration, and therefore you can easily see that this looks very this expression looks very familiar to the first definition of entropy. So then we will need to remind a couple of definitions. So firstly, we'll remind that a linear map from one sigma star algebra to another sigma star algebra is called Schwarz map if the following equation holds for each element of B. And then I would like to recall that we call the rank of A the dimension of a maximal abelian subalgebra of A, and the centralizer of A is centralizer A phi is a subalgebra in A such that phi from x y is equal to phi from yx, and we should also recall that a function of norm 1 is a function, I mean, of norm 1 is called a state. And by the way, this function of norm 1 is in our case the generalization of measures of probability measures. Okay, we have a number of properties for relative entropy, which are that relative entropy is greater or equal to 0, and it is equal to 0 if and only if the phi is equal to psi. Then we say that if psi1 is less or equal than psi2, then the relative entropy of phi and psi1 is greater than relative entropy of phi and psi2. And then, so, okay, what other interesting facts do we have? So we can decompose the following So if we have a linear functional phi expressed as a sum of some other linear functionals, we can decompose the sum of entropies of phi i's relative entropies of phi i's and psi as the following entropy. Also, we know that for Schwarz unital map, the entropy of composition of the Schwarz map with phi and Schwarz map with psi is less or equal than the relative entropy of phi and psi. Also, we know that S1 is a convex function as usual. The entropies that we have discussed before are also have also been convex functions. Then we probably can discuss the von Neumann entropy, which will generalize the entropy of not the relative entropy, but a simple dynamical entropy, but for a positive linear function on our C-star algebra. Again, we have the same function eta, and the von Neumann entropy of phi is defined as the trace of eta from the density operator of phi, which, in other words, is minus relative entropy of phi and the trace operator. Okay. Again, we have a number of statements. For example, okay. So, for example, that the entropy is less or equal than logarithm from rank A and greater than 0. S is continuous, concave, and additive. By the way, I have told you that they have all been convex, but obviously this depends on the sign that we have. Sometimes we have this thing with a minus, and then it is convex, and otherwise it is concave. Okay, then if we have a convex combination of states, then we get that the entropy of phi is greater or equal than a linear combination of lambda is times the relative entropy of phi e and phi. So this is a typo. This should be I and not 1. Again, if we have a state on A and a state phi on A and a state psi on B, then we can consider the product of phi and psi and achieve that the entropy of the product is the sum of entropes in A and B. This is the same condition. This is the same property that we have discussed for topological entropy and for dynamical entropy in the beginning of this seminar. Okay, I think I won't necessarily read this all out loud because, well, I think we can discuss a bit more interesting facts about von Neumann algebras. So we have a corollary that for a subalgebra, so that if a subalgebra B in A contains the maximal abelian subalgebra, then the restriction of the state phi on B is the entropy of the restriction is greater or equal than the original entropy, and this inequality can be further improved. We know that the difference between the entropy of a restriction and the original entropy is less or equal than the following sum. Okay, Then so the final thoughts on von Neumann algebras and von Neumann entropy are as follows. We can get a proposition that is called the thermodynamic inequality for a state phi in A and the self-adjoint operator. And this equality holds for the following density operator. And the last thought is that for two states, such that and the rank of sister algebra equal to D. If we have the following condition on norm, if the norm of the difference, no, well, I mean the distance between phi and psi is less or equal than epsilon, then we get that the difference between the entropies is less or equal than epsilon times logarithm d plus eta from epsilon. So this is pretty much all I wanted to tell you without proofs. So this is the basic ideas that I wanted to mention. Probably you would like to ask me some questions now, and then I will probably discuss with you a couple of proofs for some propositions that I have mentioned here. Again, so the main book that I have used is the one that you see on the slide. I haven't included more references for some reason. So now I'm finished with the lecture part. So are there any questions?
Well, thank you very much. Please, questions and comments.
In that case, the space of all states is just unit sphere indoor space. So you said that a state is just functional with unit norm. So it means the space of all states is just unit sphere indoor space.
Excuse me, it is very hard. I couldn't hear you well.
It's still quiet. I want to ask. So you mentioned that that the state is unit functional unit norm. So the space of it's slide 23 years 23.
Thank you.
So the space of all states is unit sphere indoor space, or we
yes, I think I agree with you.
Or we can
it is contained in the unit sphere, but of course it's
contained.
not exactly the unit sphere because we consider only positive functionals. Here it's written down that a functional of norm 1, but the correct definition is a positive functional of norm 1 is called a state.
Okay, I have probably, yes, I think I have, I haven't said that it's positive because all the functionals that we're discussing are positive linear functionals.
And the operator, the operator QF is also positive here.
So we define the relative entropy for and the von Neumann entropy only for positive linear functionals. Okay.
And
Well-
can you remind how Schwarz map looks?
Okay. What do you mean how it looks?
The definition, I mean.
Okay, so the definition of Schwarz map is that, so I think it's pretty much listed on this slide. We have two sister algebras, and the Schwarz map is a map between them, such that when we take a product of B star and B, and then so then Schwarz map lambda from that's not lambda, it's alpha from this element is greater or equal than alpha from B. I mean the involution of alpha from B times alpha from B. So these are two elements of A, and these are elements of B.
For example, if you take a star homomorphism between sister algebras, and of course it's a Schwarz map because we have an equality here. And also if you take an algebra homomorphism and multiply it by a number strictly smaller than 1, then you get again a Schwarz map. So some generalization of an algebra of a star homomorphism. My question was about infinite dimensional generalizations. So first, you told us about the classical entropy, where the algebraic picture was based on the algebra L of infinity, the algebra of bounded measurable functions on a measure space. So then you somehow then you consider the analog where our base algebra is a finite dimensional sister algebra, that is, in other words, a finite direct sum of full matrix algebras. So natural question is, are there any reasonable generalizations to infinite dimensional sister algebras, such that, for example, the L infinity algebra and the matrix algebra would be just special cases of this infinite dimensional setting. So are there any results about any results, or maybe for some infinite dimension of sister algebras, or for Neumann algebras equipped with a trace, something like that? So are there any such results?
Yes, there are such results. I can probably write down some. So I can probably write the relative entropy for general case of C star algebra, and we can discuss this definition for a bit if you would like to. What do you think about this idea?
Well, that would be maybe a good topic for a separate talk, because it's more or less immediate. The definitions are more or less immediate. So we have to take a sister algebra equipped with a trace that is a positive functional, and then to extend this somehow to this. But the question is what the question about is about the results. So are the can we generalize these results from matrix algebras to the infinite dimensional setting? So
yes, we can. So
okay, thank you.
The short answer is yes, we can generalize it.
Well, maybe sometime you'll tell us more about this.
Yes, I think this can be a good idea.
Okay, thank you.
Okay.
More questions, please. Okay.
Okay, then shall we discuss something, just some proofs for this, or probably if you're not interested, not very much interested, we can just finish a bit earlier than usual. So, well,
So does anybody want to know the proofs? Or we can nobody.
okay.
Okay, so
which statements do you want to prove?
Well, for example, well, one of the statements I wanted to prove originally, so I am not capable of reading my own slides. Okay, one of the statements was that we can indeed use the following expression instead of this one, so that this supremum is not greater than the entropy defined using the partition of unity. Another one, well, I don't feel very enthusiastic about proving the statements about finite entropy because they're quite long, especially since the amount of properties are very long, and it is very hard to to find some proof to have a reminder in front of my eyes, because I don't remember them by heart, obviously. Well, I think that I will just prove something if nobody is against it. Okay?
Okay, thank you.
Okay, so I'll stop the demonstration for a bit, and I will use so give me a moment. So so let us consider. No, this is, so let's consider the entropy as the following sum using the identity operator. No, identity. Why identity? Not identity. The indicator function. Using the indicator function of elements of our partition. Okay. Then we will consider our supremum of the following sum taken over all possible partitions of unity. Okay. No, this is not quite right. Okay, minus mu at fi. By the way, I was constantly calling this function h on the previous talk, but this is actually the capital Et, and I didn't realize that the capital Et looks exactly like h. Okay, so we will need to prove that the supremum is not larger than the previous definition, and we will take functions fi's that are less than equal to 1 and greater than equal and greater or equal than 0, and such that they are indeed partition of unity. Then we will have the following expression. So these fi's should actually take the following form. they will look exactly as some lambda ik's times the Так, я не знаю, почему я сегодня индикаторную функцию решила не помнить категорически. Okay, times the indicator function. Okay, and this equality will hold because this is the form that measurable functions will take in in lambda L infinity x factor c. No. So all measurable functions will be so they will be constant on the elements of the partition, and therefore they will take the following form as I have written. So in order for that to be a partition of unity, we will have the following equation for lambdas, and using the fact that we have discussed for a bit on the previous lecture, the previous talk, not lecture, using that of the sum is less or equal than sum of ettas, we can compute the following. Okay, we will take the sum as eta from mu of fi's minus sum of mu eta lambda ik identity operator xk. Then we can state that there is the following inequality, that this thing is actually less or equal than sum over I and k of eta mu okay. So, well, where have I stopped? Okay, okay. So we will have the following thing going on. Here's the identity. Not the identity. Okay. The operator 1x. I'll call this thing 1x lambda mu as we have discussed minus mu of eta and lambda ikx xk, which is on the other hand, so this is a big sum. This sum includes both of these parts. Okay, then we can rewrite it so that we take the lambda out of the measure mu. And by the way, we go back to our to considering this thing as a partition of x minus eta from lambda ik mu xk, and which is finally equal to sum of nu at mu xk. So overall case. So what we have achieved here is that so we have pretty much achieved the inequality that the new definition is less or equal than the original definition, because we can rewrite the original definition without the indicator function, but using mu of elements of the partition, right? Okay, this is what we have achieved, and how we have achieved it is quite clear. We have used the fact that so firstly, what we have done is to okay, one moment. So yes, I think that the main inequality, so the equalities are pretty obvious, and the inequality here I think it just so I think if we rewrite fi in the form that we have stated above, we will probably get this inequality, because here we will take summation over two indexes, and well, probably somehow we'll achieve what we wanted. Sorry, I have forgotten this thing. Okay, so so this is the idea of the proof. Probably you have understood it. So this is just pretty much the main part. Well, yes, obviously the inequality follows from the inequality from it, of course, and the other ones are just we have just used the idea that fi can be described in terms of the indicator functions. So, and actually this was the main idea. So the most essential thing that we have done here is to understand that all FIs should take the following form, and the rest pretty much follows from it. So now I think I'm finished, and the time has ran out, I think. So thank you for your attention. If you have some new questions, I can answer them.
Thank you very much. Thank you. Oh, please, questions. Okay, so if there are no questions, then we thank you very much again, and we will be happy to if sometime you'll tell us about infinite dimensional generalizations.
Okay.